Welcome to the video for Chapter 14. This chapter talks about doing hypothesis tests on whole models. I liked this quote from the textbook, so I thought I'd pull it out. It mentions that just as constellations in the night sky are a product of the human imagination applied to the random scattering of the stars within range of sight, so the patterns indicated by a model might be the result of accidental alignments in the sample. This is important because remember, when we're thinking about using the sample in our model, generally we're trying to understand relationships between the variables in the larger population, not just in the sample. And so we want to be able to assess whether the relationships we see in our sample are likely to be true in the population as well. So when we focus on doing hypothesis tests for the whole model, the hypotheses that we test are going to be that the null is that in the population, the explanatory variables are unrelated to the response variable. That would mean, in effect, that a model with no explanatory variables in it is just as good as our model. On the other hand, the alternative hypothesis is that in the population, the explanatory variables do account for some of the variability in the response. And what that would mean is that our model is, in fact, better than a model with no explanatory variables in understanding what's true in the population. So once our hypotheses have been formulated, we need to choose an appropriate test statistic that we can use to test them. Now, in the special case where we have a linear model with only one explanatory variable, then we could actually do a test to see if the coefficient, the slope corresponding to the explanatory variable, differs from 0, and that will in fact be a test of the whole model. But in general, if I have a linear model with more than one explanatory variable in it, I can do a test for the whole model either by looking at r squared. If r squared is greater than 0, then what that would mean is that the model is explaining some of the variation. So testing to see if r squared is greater than 0 is a test of the whole model. However, we generally don't use r squared as the test statistic. Instead, we use a related quantity called f. F is the mean squares of the model values divided by the mean squares of the residuals. So if the model is explaining more of the variability than is left in the residuals, then there will be a positive value of this that's greater than 1. And so testing to see if this is greater than 1 is also a way of doing a test on the whole model. So why do we use f instead of r squared? Well, it kind of comes down to this. Remember that when we talked before about nested models, what that means is that each model contains variables that are completely included in another model. So here, for instance, this model with the intercept only, that would be this one, is nested in the model that includes just x sub 1. And the model with just x sub 1 as an explanatory variable is nested inside the model that includes x sub 1 and x sub 2. So here are a group of nested models. And this one is including just as many explanatory variables as my sample size. Now it turns out, remember, when we have an intercept only model, because there are no explanatory variables, my r squared is 0. If I include an explanatory variable for every case in the data set, I end up fitting a model that perfectly predicts the responses. So my r squared will be 1. And as we can see, if I keep adding more variables to the model, I can never explain less variability than I had in the previously nested model. So if I build nested models adding explanatory variables one at a time, this R squared value will never decrease. And we can see that over here. Here we've got the number of model terms. And here we've got the R squared value. And we can see that these are strictly non-decreasing functions. Okay, so R squared will never decrease as I add things to the model. Now my F statistic, I said, could be written this way, and I'm just going to put this a little bit bigger. Now M, remember, is the number of model terms that are estimated, so that's the number of explanatory variables that we have in our model plus the intercept. And what we can see as we look at this F test statistic is that it incorporates information about how much of the variability is explained in the model versus what's left unexplained, but it also incorporates information about how many variables, explanatory variables, are included in the model. And so by doing so, it gives us a better picture of how good the model is, because remember, R squared alone is partly just going to increase if I have lots of variables in the model, even if the variables aren't particularly useful for predicting the response variable. Now, when I use an F statistic, it does have these numbers called degrees of freedom associated with them. And there are degrees of freedom for the numerator, which is just this value that we divide R squared by in the numerator of our F statistics. That's M minus 1. Since, we're talking about the number of model terms estimated, that is going to be the number of explanatory variables in the model here, because I'm going to include the intercept in M. So M minus 1 is how many explanatory variables are in that model. And then my denominator degrees of freedom, that's what I'm dividing my 1 minus R squared. N minus M is my denominator degrees of freedom. Remember, once we have our test statistic, I need to figure out a probability model for the test statistic, assuming that the null hypothesis is true. And one way that I can do that is with a permutation test. Now, the basic idea of a permutation test is that I start, as I always do, by using my sample to calculate a test statistic. So in this situation, I'm going to do a tiny example with a data set that has only 5 cases. Here they are. Here I'm considering A, my response variable, and B and C are the explanatory variables. Explanatory. And I used R to calculate an F value for this original sample. Now, remember that the null hypothesis is that the response and the explanatory variables are unlinked, and I need to try to figure out what the distribution of F statistics might look like if that null hypothesis were true. So what I'm doing is I'm thinking, okay, if they're unlinked, let's take the responses and separate them from the explanatory variable vectors. So here I've just separated the responses off. And then I need to find a test statistic that might occur if the null hypothesis were true. And I'm going to do this by randomly pairing the sets of explanatory variables with the responses in the sample. So you can see here, what I've done is I've taken these responses and I've shuffled the order of them so that they're now paired perhaps with a different set of explanatory variables. This is what's called the permutation part. Once I've got my permuted sample, I use that to calculate the test statistic. Same statistic as my test statistic. Remember, this is actually my test statistic, but this is a value of that same statistic that might have occurred due to chance if the null hypothesis were true. Then I need to repeat that many more times so that I can create a distribution of these simulated results. And so here is the resulting histogram. Right? So here showing different values of that F statistic that might have occurred by chance if the null hypothesis were true. Now, ultimately, I'm going to want to use this distribution to find the p-value. How do I do that? The p-value is the proportion of results in this probability model that are more extreme than the test statistic. Now remember, larger values for the F statistic are going to more support the alternative hypothesis. So I can find this by taking my original sample test statistic, that was my F of 2.489, and then figuring out what proportion of the results in this distribution are larger than that. So, somewhere along here, I've got 2.489, and I'm going to be figuring out what proportion of my simulated F values are out in this distribution. So in this case, when I used the tally function to count them, I found that there are 1,156 results out there out of a total of 5,000 samples that I used. That proportion comes out to 0.2312, and that is my p-value. So with a p-value of 0.2312, that's a large p-value, right? Which means that there is weak evidence that the response variable is linked with the explanatory variables. And this could mean a few different things. One of the things it could mean is that in the population, there really isn't a link between these variables at all. But another thing that it could mean is that there's not enough data to reveal the link between the variables. And with such a tiny number of cases, remember there were only 5 in this data set, that's entirely likely. And then the other thing to remember is that it also could mean that there are important covariates that haven't been included in the model. Sometimes if you include an important confounding variable in a model, then it will, once you've controlled for that variable, you'll be able to get a clearer picture of what the relationship is with the other variables. So it also could mean that your model is not well specified. I want to go through the R code for the permutation test for just a minute. So first of all, what I did for each of these simulations, remember, is I unlinked the response variable A from the explanatory variables B and C. And then I shuffled around, right? I moved the values of A and paired them with different pairs of the B and C response variables. And so that's what this is doing. What this is doing is it's taking the values of the response variable A and it's shuffling the order of them and then pairing them with the same values that I already had in the same order of B and C. So by doing this shuffling part, this part here is permuting the responses. And remember, for each of those, I calculated the F test statistic, and the linear model function is going to do that for us. And since I want a whole bunch of different reshufflings, I used the do 5,000 times to do 5,000 permutations. And then I just created an object null trials to hold them. Made a histogram so that I could look at them. And then I knew I was looking, because 2.489 was my test statistic from the original sample. I counted with the tally function how many of the number of these null trials had the F statistic greater than 2.489. It told me that there were 1,156. And then I divided this by 5,000 because I had done 5,000 total trials. So you may have noticed that this F distribution had a shape that was very skewed to the right. And just talking generally about the shape of the distribution of an F statistic, note that because we've got sort of mean squares over mean squares are always going to have to be non-negative, and certainly are going to be positive unless all of my responses have exactly the same value, which is unlikely. So it's always going to have to be greater than 0, and generally it's going to be more than 0. If the conditions are met, there are some certain conditions that can be met, then instead of using a permutation test to simulate the distribution, I could use a probability distribution called the F distribution to get the p-value. And I'll talk about those conditions in a second. An F distribution, the exact shape of it depends on the numerator and denominator degrees of freedom. Generally, they're skewed to the right. But as you can see over here, when you have a very large number of cases, sometimes your F distribution will start to become relatively symmetric and normal looking. F distributions have the characteristic that they always have a mean at 1. The conditions that are required to use an F distribution, one of them is that the relationship between each explanatory variable in your model and the response is linear. So our book doesn't talk about these conditions or about how to check them, but I thought it's something that is important and I wanted to at least mention it to you. So I could use, a scatter plot to look at the relationship between A and B and see if it appears linear. It wouldn't look too bad except for this one outlier. With a really small data set like this, it's really hard to judge linearity, because if I added, like one more dot down here, it would look like not much of a relationship at all. On the other hand, if I didn't have this dot, or if it was moved slightly up, it would look much more linear. So it's a little hard to tell with a tiny data set, but just kind of how you would look is by looking at a scatter plot. And then I can also look at a scatter plot between A and C. Here, C was a categorical variable, and so I really just have the 2 levels of it. Another thing that's important is to have the residuals be independent of each other. Generally, the way we check this condition is not by using a graph or something like that, but thinking about the way that the data is collected. If the data are collected from a random sample from the population, then theoretically the residuals should be independent of each other. Another assumption for using an F distribution is that the residuals have an approximately normal distribution. Again, this is something that's very hard to judge if you don't have if you have a very tiny data set like we did. You can see here is my histogram of the residuals. It doesn't look particularly normal, but again, I only have, 5 data values, so it's a little hard to judge. And then the last assumption is that the variance of the residuals is similar across the different values of the explanatory variables. This is usually checked by plotting the model values on the x-axis and the residuals on the y-axis, and looking to see, if I look around a line of residual equals 0, to see if the scatter looks approximately equal around it. This one looks a little bit sort of fishy. I've got these all small residuals down here, negative ones in the middle, and these positive ones at the edges, so it has sort of a pattern to it possibly. Again, with a tiny, tiny data set, it's very hard to judge. So something I'll mention is, this is if I want to use the F distribution to find my p-value. If I'm going to use a permutation test, I actually only need to make the first 2 assumptions, so I don't have to worry about the normality of the residuals or about the variance across residuals being approximately equal. So in this situation where it's so hard to be confident in those assumptions based on the tiny data set, the permutation test is probably the way to go. But if we did use the F distribution instead of the permutation test, there are a couple of, I can take a look at how I could do this. I know my F value from my original sample was 2.489. I had 3 items estimated by my model: the intercept, the coefficient for B, and the coefficient for C equals male. And so 3 minus 1 gives me 2 degrees of freedom for the numerator. And then my denominator degrees of freedom, remember, are n minus m. N was 5. There were m equals 3 values that had to be estimated for the model. 5 minus 3 gives me 2 degrees of freedom for the denominator. When I use the P, remember, is percentile, F for the F distribution. This is going to tell me the proportion that are less than or equal to 2.489. So I take 1 minus that, it gives me the proportion that's more than 2.489, and it gives me 0.2866. And I'll just point out that here on your output, when you do a summary for your linear model, you can see your F statistic is right here. It tells you the degrees of freedom also, and it tells you the p-value. So if you're fitting a model, you don't need to calculate it this way. You can just pull it right off of the output. We've talked throughout the semester about how linear models can be used to partition variance between the variance that's explained by the model and the variance that is left over in the residuals. And there's a way of looking at this called an ANOVA, or analysis of variance table. Now, to produce an ANOVA table in R, you use the ANOVA function, and the argument that goes into it is the model that you want to calculate the analysis of variance table for. So here, instead of storing my model as an object, like calling it mod1, I just put the function that generates the model in there, but you could put the model name in as well if you had stored it as an object. And so just say ANOVA of your model. And then it produces a table that looks like this. Now, the way that they talk about it in this section of the textbook, they don't show you all the different pieces of this table, right? They show us only something that includes all of the model and the residuals, where this is showing me sums of squares and mean squares for each of the explanatory variables in the model, as well as the residuals. But the thing about sums of squares is that they add, and degrees of freedom add. So for instance, if I have both B and C in the model, then the model sums of squares are going to be equal to the sums of squares associated with B plus the sums of squares associated with C. So as I go through and calculate this, I can add my sums of squares, 1.2922 plus 4.9860, and that'll give me my sums of squares. My degrees of freedom for the model, are going to be the degrees of freedom associated with B plus the degrees of freedom associated with C, or 1.1 plus 1 equals 2. Right? So as I look through and say, okay, so my model degrees of freedom are 2. The residuals are already broken out on their own, so I know the residual degrees of freedom are 2. The sum of squares for the model I just said I need to add these two values. And so that will give me 6.2782. The sums of squares for the residuals are given here. Now the mean square is just equal to the sum of squares divided by the degrees of freedom. So for instance, the mean square for the model is going to be 6.2782 divided by 2 degrees of freedom. Gives us 3.1391, and the mean square here has already been found for us. But it was done by taking 2.5219 and just dividing it by the 2 degrees of freedom for the residuals. Now the F value, when I'm looking just with the model, what I do to take the F value is I take the mean square for the model and divide it by the mean square for the residuals. So I have 3.1391 divided by 1.2609, and that gives me my 2.4896. And then we saw just a minute ago how I could use R to find the area beyond that in my distribution. So there's my ANOVA table. And again, the way it's presented in the book, they show them in this form. They don't talk about how to get from this piece to this piece. And so I wanted to do that. If I want to find R squared from the ANOVA table, remember that R squared is going to be my sums of squares for the model divided by my sums of squares total. We saw that in a previous chapter. And so if I take 6.2782 and then divide it by the total sums of squares, all right, so I'm adding these two pieces. So when I add the sums of squares, I get a total of 8.8001. I divide my sums of squares for the model by 8.8001, and that gives me 0.7134. So on the ANOVA table itself, it generally does not give you the R squared, but I could use the ANOVA table to find it. And if I just look back when I fit this model, I kind of wrote on top of it, but you can see here's my model, A as a function of B plus C. And if I look down here, I can see that my R squared value was in fact 0.7134. So just looking at relationships between some of these values from the ANOVA table and some of the output that you get from summarizing the linear model. Now, a few other important points. When we think about interpreting the p-value, remember that the p-value is measuring the probability of observing a test statistic as extreme as the one calculated from our sample if the null hypothesis is true. So it's a chance of seeing our data if the null hypothesis is true. What it is not calculating is the probability that the null hypothesis is true. And in fact, there is absolutely no good way to figure out the probability that the null hypothesis is true. So just a really important thing to remember, you cannot be thinking about the p-value as telling you the chance that the null hypothesis is true. That is just not what it tells you. Another thing that's discussed in this chapter is the issue of doing multiple tests. And doing multiple tests is extremely common, especially when model building, because often we have lots of possible explanatory variables that we're trying to decide which ones are the best ones to put in the model. And so we might try out models with a whole bunch of different combinations of variables. If we're testing at the 5% level of significance, what that means is that every test that we do is taking a 5% chance that it might make a type 1 error, which remember would mean that we reject the null hypothesis when it's true. So if I were, say, to conduct 40 hypothesis tests, and in every single one of them the null hypothesis were true, how many times would I expect to find a statistically significant result? Well, I'd expect that 5% of my 40 tests, or about 2 of them, would be statistically significant. And so I'd be expecting about 2 type 1 errors in that situation. Now suppose we conduct 43 hypothesis tests, not knowing whether the null hypothesis is true for each of them. If 5 of the tests come out to be statistically significant, it's likely that some of them are type 2 errors, because remember, we're expecting 2 type 1 errors. If I do 40 tests and there's not any departure from the null hypothesis. So it's likely that I might have some type 1 errors. It's also likely that some of those might be real relationships that I've uncovered. And the question is, how do I know which? So we know that multiple testing can be a problem, and so we should think about some strategies that we might use to try to avoid the pitfalls of multiple testing. One of them is to limit the number of tests you're doing and to specify the hypotheses that you plan to test before collecting the data, and then view any additional hypothesis tests you do as being strictly exploratory data analysis. This is especially useful if you are doing a study that's specifically trying to look at the relationship between, say, an exposure and a particular outcome. You might collect data about lots of other exposures as well, but there's one that's of primary interest to you. So you might specify in advance that you are going to do a hypothesis test for a model that includes that exposure as an explanatory variable and some other known or strongly suspected possible confounding variables, and do your test based strictly on that one model. So that would be a good option in that type of situation. If you are going to do, a handful of tests, then sometimes it's helpful to use a smaller significance level for each individual test in order to protect the overall chance that you're going to make at least one type 1 error. And one common way to do this is with what's called the Bonferroni method. There are tons of other methods to do it too, though I'll just mention, each of them with their own strengths and weaknesses. But the Bonferroni is very simple to understand. If I were going to do, say, 10 tests at a 5% level of significance, what I would do is I would take my 5% level of significance and divide it by 10, and then do each test at the 0.05 level of significance. Then overall, because I've done each test at a lower level, the chance that at least one of my tests comes out to be a type 1 error is still going to be only 5%. You can see that the number of tests that you do is quickly going to make the p-value that you need to achieve statistical significance on each one much, much smaller. And so, it does make it hard to pick up departures from the null hypothesis when you have to correct for many tests. So that's another reason why it's helpful to limit the number of tests that you're going to do. If you're going to do a few tests, then you can limit the number of tests and then also use a correction. So these can be worked together. And then the other thing that you can do is you can treat situations where you're doing multiple testing as something that is used for hypothesis generating, as opposed to really testing for relationships between the variables. So view it as an exploratory data analysis type of situation, and then use the hypotheses that you generate to collect a new sample of data. This would be called an out-of-sample test, where you're using a completely new sample to test hypotheses that were generated by doing this sort of exploratory data analysis with your original sample. And one last caution, and that is to realize that really tiny p-values tell us that there's very strong evidence that there is at least some link between the explanatory variables and the response variable. However, the p-value does not measure how strong the relationship is between the variables. And that's a really important point, because sometimes there can be very, very tiny p-values that tell you that there's strong evidence of some relationship, but the relationship between the variables can still be weak. And this is particularly true when you have a large sample size. Even a very weak relationship can give you a tiny p-value when the sample size is large. And we'll use the F statistic as a way of sort of looking at why that's true, but this is true in general of most all hypothesis tests. So we saw that our F test statistic could be written as the ratio of r squared over m minus 1 divided by 1 minus r squared over n minus m. And if I just do a little algebra, I can sort of break this into two pieces. So if I look at the two pieces, this part here is focusing on how much variability is explained divided by the proportion that's unexplained. And so this being large, this part being large, is giving me a measure of sort of how strong the relationship. But this piece, if I have a very large sample size and, a modest number of variables that I'm including in my model, this part is really measuring, how much information I've collected. How much data did I collect? So if I have a very strong relationship, then even with a relatively small amount of data collected, I can end up with a large value of this F statistic. But it's also true that if I have a very large sample size, I can get a large value over here and a large F statistic and a small p-value, because remember, my F distribution looks kind of like this, and the further out my F statistic is, the less I'm going to have out in the tail beyond it. And so even with a large sample size, even if the relationship is not very strong and this piece is very small, when I multiply it by a large value, I'm going to get a large F test statistic. So it's important to recognize that the p-value itself is a combination of things, right? It relates to how strong the relationship is and how much data was collected. And it can give a small p-value either with a strong relationship or with a large sample size and a very weak relationship. So before Thursday's class, please read Chapter 14. Complete as much of Homework 9, which is due on Thursday, as you can. Complete the Chapter 14 practice exercises, which are posted on Blackboard. And start looking for model if you're an undergraduate, or models if you're a graduate student, for your project if you haven't done so already. Thanks. Have a good day.